Morning. Whoa. Good morning, everybody. Today, I'm going to just do a couple of examples from chapter 11, conservation of angular momentum, and then we'll have some time to kind of go over the chapter 11 homework that's due tomorrow, right? What's happening in lab tomorrow? Study. Review, right? I'm not going to have anything to present. You just come in, finish up your homework, get your cheat sheet together, whatever help you need, right, to feel confident about Thursday's exam. That's what tomorrow is all about, right? So we'll see how that goes. All right. So what I want to do is play you a video. This is a definite do not try this at home type thing. Okay. This is Dr. Derek Mueller of Veritasium. Doing an experiment all about conservation of angular momentum, kind of what I was doing with that bicycle wheel, only I think they've got like a 50-pound metal wheel, right? And they're going to do some tricks with it.
I am here at the University of Sydney, where the mechanical engineering shop has built this incredible piece of apparatus for me. It is a 40-pound, that is 19-kilogram flywheel on the end of a meter-long shaft. Can you imagine trying to hold this out horizontally with just one hand at this end? It is impossible, okay? Now I'm gonna let go. You gonna be able to hold this at all?
I hope so.
Can you lift it out? Make it horizontal, hold it. Come on, just try to, I want you to hold it out horizontal. See if you can. Hold it. Oh, come on. No. What I'm gonna do is I'm going to spin this up to a few thousand RPM, and then I'm going to attempt just that, to hold it from one end and have it out horizontally.
There is a scary amount of energy in that wheel.
5, 4, 3, 2, 1, boom.
I'm going to let go with my left hand. What you'll see is that the shaft remains horizontal. You can see it going around there.
It almost looks as though the wheel is weightless. How does this work? Well, instead of pulling the wheel down to the ground as you'd expect, the weight of the wheel creates a torque which pushes it around in a circle. You may recognize this as gyroscopic precession. For a more detailed explanation, click the annotation or the link in the description to see my video on the topic. Here, I want to try something more extreme.
I'm going to try to lift it over my head with one hand while it's spinning. Wish me luck.
But before I make the attempt, Rod wisely suggests that I first check if I can lift the wheel above my head without it spinning.
Let's prove that I could lift it just this end without it spinning. Here we go. It's just kind of awkward with the hand.
Physics muscles.
Careful.
Just careful. Woo! Just barely. Oh goodness, do you even lift? Clearly I do not.
Undaunted by my lack of strength, I'm going for it. But I want to make sure that the wheel is spinning as fast as possible to give me the best chance of success.
Give it 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go! That was perfect. Now I'm going to release my left hand, and holding only with my right hand at the end of the shaft, I'll try to lift it up over my head. This is a 40-pound, 19-kilogram flywheel. Ready? Here we go. 3, 2, 1. Beautiful. Let's go again. In 3, 2, 1. Nice.
Smooth.
3, 2, 1. It feels incredibly light as I do that.
you said it felt incredibly light.
Yeah.
You know, when you're lifting, it feels light.
Yeah,
Shouldn't.
I know. Honestly, I have lifted it up with one hand when it's not spinning,
Yeah.
and it feels really hard to lift it up. Like it's a
Yeah.
big effort.
Yeah.
But with this, when it's spinning, it honestly felt like it was just,
Wanting to go up by itself.
yes. It felt like I was not struggling, like I was not putting in the amount of force that you'd think to lift that kind of weight.
I bet if you let it go, it'd crash down to the ground. That's not weightless.
We can't do that though. We can't do that.
Yeah, don't let go. And Dr. Mueller knows better, but he should have been wearing a really big helmet. The amount of energy in that flywheel was crazy bad. So why? Like, you know, what's going on there? I'll do this one on the abomination here. So he's got that long bar, right? And he's got that flywheel that's on the end of it, right? And this thing's like 40 pounds, right? 20 kilogram flywheel. And the support, right? The place where he's like holding on to it's over there, right? Gravity, acting on the center mass of the flywheel, wants to pull it down, right? So here's the weight of the flywheel. And this is where he's holding it up. There's a right? From where he's holding it out to where the center mass of the flywheel is, we've got a distance, a lever arm, a moment arm, right? So we've got an R, we've got an F, and you noticed how that thing precessed around, right? He couldn't just push it up. It had to go around in a circle. Well, that's because the torque is in a direction that you're not expecting, okay? So remember, torque is the cross product between a distance and a force. Okay, we've done cross products. We know how to calculate them. But let's talk about the right-hand rule as it applies to torques. Does anybody remember how to do a cross product with the right hand? It's the handshake version, right? Okay, so we go in the first vector, R. So we point our hands across to the right here. And then I've got to twist my wrist around so that I can bend my fingers in the direction of the applied force. Which way is my thumb pointing? In to the board, right? So the torque on this thing isn't going to be down. It's not going to be up, right? Not right or left. It's going to be into the board. So which way is this thing going to go? It's going to rotate that way, right? Rather than gravity just pulling it down, right? It's going to rotate that way. It's going to experience a torque. But you're like, so what? That's the torque. Mr. Balogh, if you just dangle something, right, from one end without it spinning, it's just going to fall. And he demonstrated that, right? They could not pick it up, right, from this end. So how is like gravity being canceled out? Well, remember that a change in momentum is equal to the sum of the torques that are acting on this thing. And angular momentum must be conserved, right? Direction and magnitude. But if we apply a net torque, right, which we are, there's a torque here, it's going to change the angular momentum direction, right? So this push, this rotational push on that flywheel will cause the angular momentum to change its direction. Didn't point it out, but when that thing's going around, you kind of have to go the opposite way to keep the angular momentum constant. But this angular momentum is pointing along the axis of rotation, right? And it's going to change its direction with the torque, which supports the weight of that flywheel. It makes it possible for you to hold on to one end and that end not to drop. If that stops spinning, it's going to drop. Question?
When we're using the right hand rule or torque, like even though we know the direction, how would we, I guess, would we write it if it's positive if it's
Well, you'd say into the page, which technically is the negative z direction, But into the page or out of the page is usually what we use in physics. Yeah. All right. So I want to do another example of dealing with conservation of angular momentum. And that's the example I alluded to before, where if you're walking up to a door, right, and you hit the door, right, you walk straight through the door, but you can also like rotate with the door. And I think the best example of that, we don't have too many examples here in Fresno because our climate's pretty temperate. But have you ever been to a building that's got like a revolving door on it, right? And you walk up to that door, right? You walk up, you're walking in more or less a straight line, but as soon as you hit that door, what are you forced to do? You have to like rotate with it until you get to the opening on the other side, right? These rotating doors are supposed to make it so that air doesn't flow too much between the inside and outside of a building. So we're going to draw the top-down view, right, of what's going on here, and we're going to attempt to use conservation of angular momentum to figure out how fast, right, you would be going after you contact the door. So we know that you're walking at some speed v, right? You're going to contact this door and start moving in an arc with it. We want to find that final speed after the collision. I guess this is closer to a real collision, isn't it? Or what we consider a collision. So here's the revolving door, top-down view. It's got a, it's got the axis there in the middle. Here's you coming in. So this is kind of like a before picture, right? Conservation of momentum. We always have like a before, during, and after kind of thing, right? Thank you. And then, like after the door it was like it started here, but now the door's like over here, right? And you're rotating with it. So this is kind of what we want to set up. And start in the middle of the sandwich, so to speak. We're going to conserve our angular momentum. Okay, so this is kind of interesting. After the collision, is there angular momentum? Is anything rotating? Yeah, absolutely, right? You, the door, everything's in rotation, isn't it? But what about before? Is anything rotating before? No. Actually, yes. We did a little quiz on that, right? Things moving in straight lines can have angular momentum. So if we take a look right at the point of impact, right, where you have hit the door, right, at that instance, you are, let's say the whole door has a length L, right? You are at L over 2, away from the center of the door, and you have angular momentum. Remember, so this is like angular momentum of the person, right? The door, does the door have any angular momentum to begin with? Is the door rotating before the collision? No, it's not doing anything, right? So all we've got is the angular momentum of the person. Afterwards, we have the angular momentum of the person plus the angular momentum of the door. So we know all those different parts. But how do I write down the angular momentum of the person? What was our way of doing it when we had like the most, I don't know, broad or most applicable version of angular momentum? First of all, do we know the moment of inertia of a person? It's not on the table, is it? So we just use mr squared, right? But even before so remember, with angular momentum, we've got choices, right? We can use r cross p, which is scary because it's a cross product, right? We can use I omega, and we can use mvr. Both of these, work for circles, right? The r cross p works everywhere. the I omega and the MVR both work for circles. So, are these going to help us? Right at the point of impact, is there any kind of circulation of the person? They were moving in a straight line. They've now hit the door. What are they now doing? They're starting to move in a circular path, aren't they? So we could use I omega, mr squared times, right? But we can also use MVR. Doesn't matter, but they're equivalent. I've showed you how those are equivalent before. So we're going to set the moment of inertia of the person equal to MVR. Afterwards, okay, you know what? We'll just leave it as MVR. We'll say that we know the speed v, we know the masses, all that kind of stuff. All right, so after the collision, right? I'm kind of looking sort of here now, right? I kind of want to write it as I omega, right? I person omega. Just again, because now it's really, before a person was moving in a straight line and then it starts to rotate, right? So, and then what are we going to do for the door? Do we have anything on the table for the door? Where's my table? Got a table right there. I mean, you know, C and D are, just don't look at C and D. Besides C and D, is there anything here that looks doorish? Not really, right? I mean, the problem with C and D is like, we're not rotating around any of those axes, right? I mean, you could say that D would be a door like that door right there, right? Because it's rotating along one edge. But my door, right, is rotating around its middle, where A is like really tiny. B's the length of the door. So this door is actually more like a slender rod, right? And you're like, but Mr. Balogh, doors aren't slender rods. Well, they're close enough, right? The mass, right, is extended down, but we take care of that with the big M, right? C doesn't really apply again because doors don't spin. Doors are spinning like that. I want to know that ride. It sounds like fun. So I'm going to cheat a little bit, and I'm going to use 1/12 ml squared. All right, where was my work? Come back. Right there. So we're going to use a little bit of weirdness, I door omega. And I'm going to say I door is equal to 1/12 ml squared. That's the mass of the door. This I person, we already said, was mass of the person, and they're at L over 2 squared. That's the distance, right, mr squared. And I think we've got all the pieces parts now. And mass of the person, L over 2 quantity squared, times omega, right? It's moment of inertia times omega, plus 1/12 mass of the door, L squared, times omega. Why is the omega of the person and the omega of the door the same? They're stuck together, right? They're moving together, so they're going to be the same. All right, factor out the omega. So that's omega plus the first term plus the junk from the second term. I don't want to rewrite it. MVR, and then I take my MVR and I divide by the junk. MP, L over 2, quantity squared, plus 1/12 mass of the door, L squared, equals the angular speed that we're going to have. So what do we need to know? We need to know the mass of the person, how fast they're walking. We know that the distance that they strike the door is L over 2. Need to know mass of person over. Do we got that? And then we need to know mass of the door, how wide the door. Yeah, right? And that'll tell us what the omega of the person will be when they strike the door. So just using conservation of angular momentum and a little bit of math to get through that. I know I buffalo you guys repeatedly with how fast I do math, and I'm not going to apologize for that, but it is what it is. All right. I think that was it. That was it. Okay. What I want to do now, that was the end of chapter 11, by the way. Let's talk about chapter 11 homework. I don't know if I'd ask for a show of hands or not, but how many of you just gave up on this one? Right? Okay. It's like, ah! Okay. So, what is the problem asking you to find? Torque. It's asking you to find torque, but specifically a torque that is what direction? Parallel to the y-axis here in part A, right? Okay. So in this picture, the y-axis is up, as it should be, right? Okay. So x is to the right, y is up, and z is coming out at us, right? And we have to look at all of these torques, all of these forces, one at a time. All right. I find sometimes that it's a bit easier to draw these pictures flat. So let's take a look at, I'm just going to draw an x and a y-axis up here on the abomination board. Okay? And if I take a look at this point A is going to be sitting like right here, right? In the xy plane, according to that picture. So all of the forces are acting, forces 1, 2, and 3, 1, 2, 3, are all acting at point A, right? Okay. So that means where's the moment arm? Where's the distance from the axis of rotation? Like where do we start that? Where do we end it? Figure shows torque about the origin. What are they trying to tell us about where we start the R that we need for torque? It starts at the origin, right? It starts right here, and the R vector goes up to reach point A, right? So there's our R vector. Now we've got three forces, right? The first one kind of hard in the way I've drawn it here, but it's pointing kind of out at us, isn't it? So if I do my right hand rule, take your right hands out, right? We got to practice, right? The way you learn the right hand rule is just by doing it a lot, okay? So again, we are doing torques. Those are R cross F, and they want directions, right? So we're going to handshake. We handshake in the direction of R, so you want to hold your hand up at an angle, following R, and then we need to get our fingers to bend in the direction of force number 1, which is coming straight out of the board, isn't it? So I get a torque. My thumb is like pointing this way, like kind of down and to the left, or right, okay? Is that in the y direction? Not at all, like it's not even close, right? So number 1 definitely is not it. Okay, 2 and 3 are easier to draw here, right? So here's 2, here's 3, right? Those are the forces. I can just draw them right on my diagram, okay? So again, we can use our right hand rule. So for 2, I shake in the direction of R. I rotate my wrist around so that my fingers can point down. Which way is my thumb pointing? In. Which way is in? Yeah, into the, but would X, Y, or Z? It's negative Z, isn't it? That's not Y. Okay? What about number 3? thumb ends up pointing in to the screen. So are any of those Y? No. Okay. How do I deal with 4, 5, and 6? All right, I'm going to rotate the picture a little bit. This is going to be like a top-down view of that three-dimensional picture that they have right there. Okay? Which means that this is the x-axis and this is the z-axis. Do you see the rotation that I did there? In their picture, right, they've kind of got the z-axis coming out at us. If I sort of tip this up, right, and redraw it, x is here, z. Now where's y? The y would be coming straight out at us, right? So this is just going to help me visualize like where my point is in space. So here's my point B. Again, the r vector, starting at the origin, going to point B. And then I have 3 more forces, 4, 5, and 6. So 4 would be pointing, like in the diagram, it's pointing straight up. In my drawing, it would be pointing straight out. So if we go like that, and I go out, then my thumb ends up pointing in some weird direction down here, doesn't it? Is that the y-axis? No. So 4 is not it. I'm getting nervous now because I haven't checked any boxes. 5 and 6. So 5, where's 5 go? 5 is this way, and 6 is that way, isn't it? Okay. So I go down, I'm going to do 5. I go down in R. I rotate my wrist so that 5 can kind of come up like that. Oh, which way is my thumb pointed? Pointed out. And what is the out direction? It's the y direction. Better check that one. What about 6? Oh, what's my thumb doing now? Pointing out, which is the y direction, isn't it? So I think those are it. Rank. Okay, well, we won't do that one yet. Let's just, I know you guys always hit submit. Got it. It's always good. Okay, so I'll let you guys figure out the rankings of the magnitudes of those. I wanted to use this more as an explanation or a practice for the right-hand rule. Now, there was a bit of a shortcut on this one. How do you get a torque in the y direction? What has to be true about this vector and this vector? They have to be perpendicular to the thing I'm getting out, but they can only live in the xz plane. Right? What's the only direction that is mutually perpendicular to y? X and z. So I can look at all of these and say, okay, well, 1, 2, and 3. 2 and 3 are in the xy plane. Am I ever going to get a y direction torque? No. Number 1's in the yz plane. That's not going to work either, right? I can only have distances and forces that are in x and y only, whatever they are, x and z only to get a y, right? The whole nature of a cross product is to return a vector that is perpendicular to both of them. The problem is saying it has to be along the y-axis, right? The only way for it to be along the y-axis is for these two to only have x and z components. And so just looking at the diagram, I can go, well, 4 doesn't work. 4 is in the yz direction. But 5 and 6 and the radius vector from the origin to B, those are all laying in the xz plane. So no matter what combination, no matter what direction 5 and 6 point, and no matter where B is in that plane, what direction will the torque always be? Positive or negative y. It has to be because of the nature of cross products. So remember, cross product gives you perpendicular vectors to the two that went into it. All right. I'm going to let you work those out. You can ask me questions about them tomorrow, okay? Yeah, that's conceptual. Okay. This is a conceptual one. That's good. There's a lot of conceptual. Why was there so many conceptuals on this homework? There's a lot of concept behind the right-hand rule, right? And its application. Okay. So into the actual problems here. And I just kind of want to give heads up, right? Drop some hints, help you out. And then I'm going to let you ask questions here in the last half hour of class. But let's kind of go through here. So I think one of the challenges of chapters 10 and 11 is that you have 4 toolboxes to consider, right? And so I've had a lot of questions in the last week. Well, Mr. Balogh, how do I know how do I know it's kinematics? How do I know if it's angular momentum? How do I know if it's torques? Well, the answer is context. Like, what are they asking for? So let's just review, like, there's something that is unique to each of those toolboxes. If there wasn't, we wouldn't need the toolbox, right? We would just be replicating things. And there is a lot of carryover and similar symbols and things like that. But there is one thing that kinematics, like, kind of depends on, so to speak, right? And what is it? Acceleration, right? Like acceleration is everywhere in kinematics. And you might say, but Mr. Balogh, Newton's laws have acceleration in them. And that's true, but what does kinematics not concern itself with? What's the big concept that's missing when it comes to kinematics? Forces, right? Kinematics doesn't really care about forces at all. It's acceleration, velocity, time, right? And so dead giveaways to kinematics, if you don't care, if there's no forces, like you're not being asked to identify a force, you're not being asked to figure out a force, right? Then that's going to be either momentum or kinematics. And quite frankly, I do kinematics first because it's easier, right? And how do you know when to use momentum? What has to be happening? There has to be some sort of interaction, right? Kinematics is what takes place when your acceleration is the same. But as soon as you have an impact, an interaction, right? Now what we've got is a conservation of momentum problem, right? So kinematics, the giveaway there is you don't care about forces, but you do care about time, which means you care about acceleration and velocity. All right. How do you know if you got to use Newton's laws? They're asking you to find acceleration from forces. Or you're being asked to identify a force, right? And of course, if you're being asked to identify a force and you don't know the acceleration, you might be able to get the acceleration from kinematics, right? They feed into each other. But key to knowing that it's Newton's laws is knowing, like, if they're asking you to identify force. Solve for the tension in a string, or given the tension, find the acceleration, something like that. If the objects are connected together with string over a pulley, what do you know? It's not a good day, right? It's just not going to be a good day. So that's going to be a Newton's second law problem in rotational or linear form. Okay, so momentum we talked about. There's got to be some sort of collision interaction where we're trying to find the velocity before and after. And then energy. How do you know when you have to use energy or not? What does energy not care about? Give me a hint. It's what kinematics cares about. Acceleration doesn't enter anywhere into conservation of energy. And neither does time. If you don't know anything about how long it took for something to happen, if the acceleration isn't something that you need to know or need to solve for, then conservation of energy is the answer. Could be momentum, but again, you know it's momentum when there's some sort of collision. An angular momentum, you know, when there's a change in moment of inertia. So you look at context, you look at sort of what you've been given, what you're being asked to solve for, and you find the appropriate tool. And part of that is just knowing the strengths and weaknesses of the toolboxes. And the analogy of you don't screw in a screw with a hammer is very applicable here, right? The screw could be being asked to solve for, say, the time it takes for a car to speed up. And if you reach for Newton's laws, you're trying to hammer a screw, right? And it's gonna work eventually. Like, can you drive a screw with a hammer? I mean, sure, if you work at it hard enough, it's gonna go in. It's not gonna be pretty, right? So, and you run a risk of hurting yourself. So looking at this problem, that was a long way of saying, how do I know what to do? What's the problem asking me to find? Angular acceleration. So that's like finding regular acceleration just in circles. They're giving me speed, some diameters, a distance that it comes to stop. They're giving me an angular, like complete turns of a tire. That's like a theta. What does this sort of like naturally feel like? It's kinematics, right? They're not asking me to find a force. They're not telling me about forces. The car hasn't really hit anything, right? I would love to be able to do this with energy, but the problem is they're asking me for acceleration. By the way, when I have no idea, my first thing that I reach for is energy, okay? I just always try energy first anyway, right? When I have no clue. But here, energy wouldn't have worked for me because they don't tell me anything about like the friction in the brakes or anything, right? There's no coefficients going on here. This is kinematics, right? And you'll want to work it with angular kinematics and a little bit of Google Translate to go back and forth between the linear motion of the car and the fact that the wheels on the bus go round and round, so to speak. This was mean of me. I will admit, this was me looking at the picture going, because what do you know you have to do after that cylinder comes off the roof? As soon as it comes off the roof, what is it doing? Projectile motion, right? So right back to chapter 4. Yeah, got to remember some chapter 4, right? Just perfect opportunity to do some review here. But before it leaves the roof, so to be able to do the free fall portion, you know how fast it's coming off the roof, right? And the problem is written to kind of hold your hand a little bit, right? Because they ask you, how fast is it coming off the roof? They just say, what's the angular speed as it comes off the roof? Once you know the angular speed that this thing comes off the roof, you can find how fast it's going, like its center of mass speed, which is what you need for the free fall portion, right? Because once it's in free fall, does it matter if it's rotating or not? Makes absolutely no difference, right? So how do we go about finding how fast it's going when it reaches the edge of the roof? Again, our choices are a kinematics problem, a Newton's second law problem, an energy problem, or a momentum problem. Are there any of those that we can eliminate right away for the section where it's on the roof? Newtons. Why? Well, okay, sort of. Could we draw a free body diagram? We could. We could find the, okay. The one we can eliminate right away is conservation of momentum. Why? We're not we're not running into anything, right? We're not trying to find speed like before and after a impact or anything like that, right? So momentum's out. Newton's second law is too difficult to contemplate right now. I don't want to do it, right? So that leaves two. That leaves energy and kinematics. I'd go for energy first. It's just easier and faster for me to set up an energy problem. And we can, is it losing gravitational potential energy as it rolls down? Yeah. So it starts with potential energy, it ends with kinetic energy. What kind of kinetic energy does it end with? It's got rotational because it's rolling, and it has translational because its center of mass is moving, right? And I showed you how to do that in lecture where I had the bowling ball, I think, rolling down the hill compared to the one that slid down the hill. So this problem, you do conservation of energy in the first part where it's on the roof. Once you find out how fast it's going at the bottom of the roof, chapter 4, kinematics problem. And away you go. I love this problem. I love it. Oh. Do I rob you of the joy that is figuring this problem out? Because there's something amazing happens in this problem. I'm going to do part A for you. I'm sure none of you are going to object. Okay? I'll let you do part B, right? But I'm going to do part A for you because this is a great problem. This is a fantastic problem. Okay. Let's get, give me a second. I got to get set up here. Let's just get the raw problem here. Copy and delete. So here's the question 8. Get all the whole thing on there, Mr. Brown. Okay. All right. Kinematics, Newton's laws, energy, or momentum. Eliminate one of the 4. Momentum. It's not colliding with anything, right? Okay. Eliminate something else. Kinematics. Why not kinematics? I'm not told anything about time or acceleration, right? Okay, you've got Newton's laws and energy left. Which one are you going to pick? Energy, why? Because Newton's laws are hard, right? And if you can do it with energy, do it with energy. Don't draw a free body diagram if you can avoid it, right? So, this is physics thinking, by the way. Find the easiest way to solve the problem, which usually is make an engineer do it. Okay, so where's my initial point? Where the ball starts. And then for part A, my final point's going to be right there, isn't it? Right at the top, okay? Because they're saying something about, it's on the verge of leaving the track. I'm not sure what I know what that means, but I'm going to figure it out later. Okay, so where am I going to put 0? Yeah, I'm not going to put it at the final point. I'm not going to put it at the initial point. I'm going to put it at the lowest point in the problem that everything is referencing, right? See how they're referencing h from the ground there? Okay, so I'm actually going to put my 0 at the very, very bottom. And then I'm gonna run with it, right? Work other plus energy initial equals energy final. Let's see where this gets me and what I can do here. Work other. What does work other mean? Is there any friction? I mean, technically, yes, there is because it's rolling, right? But it says it rolls smoothly, meaning that this is perfect rolling motion. And while we recognize that there is static friction there, that's not what goes into work other. What goes into work other is kinetic friction. Is this ball sliding? No. Is there air resistance? No, none of those things are here. Are there any methods of propulsion? Like, is there a little rocket motor on the ball or anything? Like anything that's not gravity or a spring or rolling? No, there's nothing in this problem. So that's good. I don't have to worry about that. All right, what kind of energy does it start with? Potential. Gravitational potential energy. There's no springs in here, right? Okay, when it gets down to that final point, what kind of energy does it have? It has potential? Yeah. It's got mg 2 big R. Oh my gosh, what happened? What happened? What happened? What's the height that the thing is at? Twice the radius, the diameter of the circle, right? It's not the radius. It's okay. This distance right here is 2r. There's an r and there's an r, so there's 2r. Okay. So that's the potential energy it has. Now, does it have kinetic energy at that point? Yeah. What kind? Yes. 1/2 mv squared and 1/2 I omega squared. Oh boy. Okay. Now I take another look. What am I solving for? What's part A asking for? Find the height. Okay. Find this. Right? So that, okay, divide by mg. I'm done. Okay. But what do I know? Did I know the mass? Yeah. Yes. I know what planet I'm on. Do I know the big R? Yeah. Yes. Oh dear, I don't know V, and I don't know omega. Moment of inertia. Okay, so they're telling me something. Solid ball. So if I go to the table, my moment of inertia is 2/5 mr squared. Is that right? Because the thin shell is 2/3. I practically memorized the table because it's just so useful. How do you find the moment of inertia of a cow? No. No, if you're spinning a cow on its axis, and I'll let you choose what axis you're going to spin it on. How do you find the moment of inertia of a cow? It's easy. Assume the cow is a sphere. 2/5 mr squared. Right? Have you not heard of the spherical cow? Ask a physicist to find the volume of a cow. Easy, 4/3 pi r cubed. Right? Engineers will get all bent out of shape about the shape of the cow. Physicists are like, it's a sphere. Cows are roughly. All right. So this is a 2/5 mr squared. Okay. Ooh, is that a different R? Yes. It's the radius of the ball, right? It's not the R, which is the radius of the track. So I gotta be careful. I got multiple R's flying around here, don't I? And I've got some weird thing that is telling me that I'm not sure about either. We'll get to that later. Let's see what happens when we get stuff chucked in here. Now, yeah, let's just chuck stuff in and see. Let's see where we get. Because it's going to start looking, I have a feeling it's going to start looking bad. mg2r plus 1/2 mv squared plus 1/2 and then 2/5 mr squared omega. Okay, this is getting worse. Oh! What's something that I have everywhere? All gone. Well, that made things a little bit easier. Right? Okay. I can keep solving. I'm going to just solve for h here, and then we'll get back to things. If I divide by g, then that g goes away, doesn't it? But I pick up another, I'm dividing by g, right? So I got to do it there, and I got to do it there. But that's okay. Those are just numbers. So finally, I've got my h. I've got 2r, 2 big R, plus 1/2 m v squared over little g, plus, this 2 and this 2 go away, don't they? They cancel each other out. Plus 1/5 r squared omega squared all over little g. I got too excited with one of my m's, didn't I? I can get rid of that one. Okay. Look a little bit better. I know, okay, so I'm just kind of going through here. What is this? It's a number. How do I know it's a number? Because they gave me the numbers for it, right? So I'm not looking at, this I don't look at anymore. It's just along for the ride. Do I know the numbers here? No, I don't know the v. And again, same thing here. The omegas kind of throw me off. So how do I deal with like having a v and an omega in this problem? Google Translate, right? So I can go ahead and say, look, I know that the relationship v is equal to r omega for something that's rolling, which means omega is going to be v over r. So this is going to get rid of my omega for me just a little bit, isn't it? So this is going to be, this term is going to be plus 1/5 r squared over little g, and then this is going to be v squared over r squared. Ooh, ha, 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 ha. The little r canceled right there. Oh, life is so good. Oh, so good. H equals 2r plus 1/2 v squared over little g plus 1/5 v squared over little g. If I have 1/2 of an apple and 1/5 of an apple, how many apples do I have? 7/10, right? I have 7/10 of an apple. Plus 7/10 v squared. Whoa! How did this turn into this? Magic. Physics. All of the above. This is so cool. I love it. I love it. I love it. Okay. But what's V? You haven't told me anything about V. Am I going to snatch victory from the jaws of defeat, or am I stuck here? What are they telling me? The ball is on the verge of leaving the track. Oh, the normal force goes to 0 at the top of the track? Oh, wait, okay, so where have we done that before? Oh, okay, all right. The fear's beginning. Back before, it's not a circle. Not even the AI could deal with that one. Before, when we were doing the roller coaster upside down, so this is my ball upside down, right? You can tell it's a ball because it's a square. mg's acting downwards, the acceleration is towards the middle. And if it's going to leave the track, I mean, normally, there would be a normal force acting down. But if it's coming off of the track, then what happens to the normal force? Boom. So what have I got? I've got a statement that says MA equals sum of the forces. The only force I have, if it's coming off the track, is gravity. The M's cancel. Because it's moving in a circle, I know that the speed squared over the radius of that circle is going to be equal to the acceleration, which is that. And which R is this? It's the radius of the loop. Not the radius of the ball, it's the radius of the loop. So that means V squared is equal to big R times G. So that means this h is 2r plus 7 over 10, big R times g over little g. The little g's cancel. I just solved the problem for every planet in the solar system and the universe. And what's more, this h, if I have 2 apples and 7/10 of an apple, then how many apples do I have? 27/10 of an apple. Isn't it beautiful? How do you get from something so bad to just this? Physics. Let's see if it's right. It better be right. If it's not right, I'm going to be really mad. Let's see. Can I get my iPad 27 over 10 times, what's my 0.13 equals? You going to detect that as math? Oh, it says it's still thinking about it. Okay, it realized what it was. No. Solve. It's equal to 0. Oh, golly. We'll get there someday. We will. No, now it doesn't think it's anything now. Okay, what's 27 over 10 times 0.13? 0.315? 0.351? Yay! Okay, meters, right? 0.351. This better be it. This better be it. Well, I didn't put my units up, but it's right. Love that problem. Just love that problem. It's just so, I don't know what the word is. Elegant? A lot of you are looking at this going, this is not elegant, Mr. Bale. I had no idea what just happened, but. Yeah! Oh my gosh, this is wonderful. What are you talking? Okay, so this problem, remember, I over-prepare you for the exam, right? So if I were to put this on the exam, I probably would, I wouldn't have you be doing this part with Newton's second law in it, right? Okay? I'd probably just tell you how fast it's going or something, right? Just to give you a little bit of a shortcut over there. But certainly this conservation of energy statement, right? Just sort of really focusing in on the central part of this problem, which is this conservation of energy, right? In rolling motion, that kind of stuff. Yeah, absolutely. Expect you to be able to identify whether or not there's any work, identify what the potential energy is before and after, what the kinetic energy is before and after. Yeah. How I got this? That was from chapter 6. You can go back to chapter 6 notes for the roller coaster. Yeah, this right here is Newton's second law. Ma equals sum of the forces. Right here? It's centripetal acceleration. Centripetal acceleration is v squared over r. Yeah. So a lot of pieces to put together in this problem. Again, a level of difficulty above what I'd expect you. I mean, if this is the only problem you were doing in 70 minutes, sure, yeah, I'd make you do, right? But you have 7 problems to do, right? So I've got to make sure each one of them is roughly 10 minutes long for you. How have I been doing on that? Now that it's too late for me to rewrite the third exam. You have time. It's okay. Yeah, it's still a couple days. Have you found that the average time on a problem is about 10 minutes, or is it way out of whack? Way out of whack? It's taking you longer than 10 minutes on per problem on the exam? On the exam. Yeah? Yeah, no, everybody always wants more time on the exam no matter what. So, all right, we'll see what happens Thursday. I think it'll be okay. But what you simple questions, right? Do I put my shoes on before or after I put my pants on? That's the level I'm working at, Mr. Balogh. All right, let's go. You can do part. I'm gonna let you do part B. Depends on the day. Oh, cross product. Like instantly, I see IJK, and I'm like, all right, this has got to be a cross product, right? So, good practice for doing your cross product. Oh my gosh. Is this where I leave? Are you guys going to kill me? There was a bit of an emotional response here. I don't know. What was okay? They're asking me for moment of inertia of the assembly. What are these things? Where do I go on the chart? These are just little masses, so they're mr squareds, right? So it's going to be md squared plus m2 quantity 2d squared plus m3d quantity squared. Sounds like we're going to a movie theater. 4dx, whatever. Magnitude of the angular momentum of the middle particle, mvr, where r is 2d. And the magnitude of the angular momentum of the assembly, well, we just found the moment of inertia of the assembly, so it's I omega. Why was this so hard?
Because the chapter 10 version where we had the same.
Oh, you were remembering. It was the post-traumatic stress disorder. Okay. This looks like fun. Oh, ooh. Oh, they're asking about a lot of stuff. Speed, kinetic energy. So that means I'm doing energy, right? But then they pull along the pole. What are they doing? What's changing if they... The distance, which means the moment of inertia is changing. What problem has it now become? This is an angular collision, right? This is conservation of angular momentum. So this problem's sounds like it's got, like you got calculated energy. Maybe not do conservation of energy. They just say the kinetic energy of the two-skater system. So it's 1/2 I omega squared. And they want it before and after. But that pull, right, is that change in moment of inertia as they come together. That's definitely conservation of angular momentum. Okay, my brain stopped after the first. Brain stopped somewhere in the first sentence. Oh, this is the one, the two disks coming together that I talked about, like the transmission of a car, right? Very similar to a transmission of a car. So again, they come together and start spinning together. So what kind of problem is this? This is conservation of angular momentum again. Ooh! What just happened today that could possibly be related to this? Not the video we watched. The door problem, right? So instead of a person walking into a door, don't embed yourself in the door, but you are connected to the door, right? So instead of a person running into a door, this is a bullet running into a block rod. And so they tell us the moment of inertia of the block rod. No, they want us to find the moment of inertia of the block rod bullet, right? So what are you going to do for moment of inertia of the bullet? It's just mr squared. And the block, they tell us anything about the block? Just the mass of the block, right? So that's going to just be the block mr squared. And, oh yeah, it says, treat the block as a particle. And then the rod. It's attached to a non-uniform rod. Rotation inertia. Oh, of the rod alone. They tell me the rod. Okay, fine. So it's just the 0.0557 plus mr squared of the block plus mr squared of the bullet. Moment of inertia done. If the angular speed after the impact, okay, I showed you how to do that with the person running into the door. Very similar. Set it up, derive your equation, plug in your numbers, and away you go. I hope that was helpful. Yes, no? Are there any, in the last 10 minutes, any questions that must be answered before tomorrow? This is how you like help on homework? Just tell you what to do?
Yeah, because then I see similar problems.
Yeah. Yeah. It's good. Good. I had a little bit extra time to do that today, so that's good. All right. We can end there. If you want to come up and ask me questions, that's great. Otherwise, I will see you tomorrow as we review and get ready for the exam on Thursday.